be in a room with this many people who are all kind of studying and interested in this topic is really incredible. And I'm just looking forward. I hope this can be kind of playful and lively for all of us over the next few days. So I'm very curious when it comes to AI and hybrid intelligence systems, where these systems derive their purpose. Systems like this are goal-directed systems. Libby invited me to talk on some topic, and since you're all highly intelligent, I didn't want to talk about anything too technical because I knew you'd figure out, different mistakes that I made. So I thought something that would allow us to just kind of be visionaries together. So when we're talking about the opportunities that exist today, we have these new ingredients. We have AI, which suddenly can do things it couldn't do before. It's really good at synthesizing text and creating images like this one. And I want to acknowledge my colleague Maggie Lane, who was the interface between me and DALL-E. So thanks for all the help with that, Maggie. So we have AI, we have augmented reality, which is still trying to get traction with the Apple Vision Pro. I think it's going to be completely transformative. It's going to change everything again. And we have hybrid intelligence systems, these concepts about these tried and applied concepts combining humans and machines in new ways to solve problems that can't be solved in any other way. So each of these capabilities on their own are incredibly disruptive and transformative. But when we start to think about how we can combine them and what we can do if we combine them, and I hope you'll help me think about this over the next few days, it seems almost unfathomable to try to figure out what the future looks like. So one of the first, questions that arises is this idea of what is the intended purpose of hybrid intelligence systems? Who gets to decide what that purpose is? And based on whose values? And then, of course, the other natural question that arises is, if we all agree on some application of hybrid intelligence, how do we know that it's going to actually do what we want it to do? And if it does, what are some potential unintended consequences or secondary effects that might arise? The combustion engine seemed like a great idea, and we all still benefit from it in different ways, but obviously it's had some unintended consequences at a scale that we probably didn't realize at the outset. Just for perspective, this was a demo from December 9th, 1968, exactly 1 year before I was born. Does anyone know what this was a demo of? Or who demonstrated this? Yeah? Anyone? Yeah?
Douglas Engelbart.
Yeah, exactly, Douglas Engelbart. Really an incredible visionary. And I had the honor and pleasure of learning about his vision from his daughter, Christina Engelbart, who runs the Engelbart Institute and who was kind enough to join me at a workshop in 2014 where we tried to bring together people across disciplines to talk about human computation. What she explained to me is that the mouse, which is what Douglas Engelbart was demonstrating, was not just supposed to be a clever new interface to a computer, but it was based on his vision about augmenting human capabilities. The idea is, how do we get humans and machines working together more fluidly so that we can actually enhance collaboration among humans to solve problems more effectively? So Douglas Engelbart invented the mouse not just so we could have a convenient interface, but so that we could actually work together more effectively. And so I love this quote. Engelbart promulgated a philosophy of bootstrapping in which each experimental transformation of the socio-technical system, obviously he didn't have the word inversion at the time, introversion, so in which each introversion of the socio-technical system that was the NLS was his abbreviation for online system, again this was 1968, would feed back into the system itself, causing it to evolve and presumably to improve. So this is a really powerful concept. We have technology that helps us work together and solve problems more effectively. What if we use that capability to help us improve that capability so we can be increasingly more effective at working together and solving problems? And this is the bootstrapping idea. So how could we use hybrid intelligence in bootstrapping fashion to collectively identify applications of hybrid intelligence that we can agree on and predict its actual effects? So the first part of answering this question is the purpose question, right? Where does purpose come from? How do we achieve consensus? How to use hybrid intelligence systems? So I'm sure you're familiar with this concept of the homunculus. Where does the human get their drives and their motives? What decides what they should do? And of course, it's a tautology, because then the next natural question is, how does the little guy inside the bigger guy get their own motivation to do things? So it's kind of like a fractal. You can see a person inside a person forever. But of course, when we're talking about machine-based systems, where do they get their purpose? If they're programmed in, they're programmed by a human. And if they're not programmed in, they're being directed by a human or many humans. And what happens when suddenly everyone in the world has access to this capability, and people are individually and collectively using these capabilities to serve either their own personal agendas or what they believe to be societal agendas? I'm sure we all agree on what's best for society. So, what are some specific examples of how we could use hybrid intelligence to help us set goals and mediate conflict? One example is collective decision making. This was done about 10 or 12 years ago in San Jose, where Luke Homan had this idea to work with the city of San Jose, invited, I think, 300 people to come to a big banquet hall, and they put about 6 people at each table, and each table had a mediator and someone sort of trained to help with the collaboration. And they said, okay, San Jose has about $60-some million to spend, and we're going to give you monopoly money. You're each going to have a share of this money, and you can spend your money in the ways that you think make the most sense. So then there was this aggregation happening at each table, and then ultimately the way that people chose to spend their money was then kind of funneled up into a final recommendation to the city board. So this is one example of a process for collaborative governance and decision making. Another topic that comes up is the idea of collective ethics or values. Obviously, groups of people have different value systems. They can be based on location and culture. They can be based on political ideology. And then each of us as individuals has our own variance in values relative to everyone else. No two people probably have exactly the same values. This is actually a project that Libby and I have been working on. And so we were interested in trying to figure out a way to reconcile values when they're different in order to come up with a system to evaluate new emerging technologies like AI and hybrid intelligence for ethical, risks and issues. So part of that entails saying, if we all have different ideas about what's right or wrong, how do we come up with a set of appropriate ethics? And it turns out that in economics and game theory, there are some neat ideas. So one of these is quadratic voting. And in this idea, each person gets a bunch of credits that they can apply, kind of like the San Jose budget games, where say you have 100 credits, then you can apply those to vote on different issues, ethical issues. The idea here, though, is that it's weighted in such a way that if you want to apply more votes, it costs the square of the number of votes in order to apply that. And that kind of mitigates both majority tyranny, but it still allows minorities to be more influential in the issues that are particularly important to them. So this could be applied equally to budget games, to value reconciliation. So these are methods that we could potentially tap. How else could we use some of these new technologies to help us come up with collective purpose? Well, we can go to a large language model like ChatGPT, and we can say, okay, we have these toy problems in economics, like the prisoner's dilemma. How could we apply these to help us make better decisions in the real world collectively? And then it'll come up with all kinds of different historical applications of that, because it's so good at synthesizing information. And of course, one of the challenges is to better understand what can these technologies do well, and where do they fail. And I think this kind of synthesis is one of those areas where we can actually get some help in figuring out, how to be more effective together in reconciling our values and our decision making. Okay, so there's this aspect of how do we come up with a shared purpose, and how do we use hybrid intelligence to help us with that? So then there's this other question of how do we use hybrid intelligence to help us with collective reasoning, for making predictions, for modeling the world. so that if we come up with an idea of, okay, this is the problem we want to solve, and we come up with a potential solution that maybe involves hybrid intelligence and AI and augmented reality, how do we know what kind of impact it's going to have and what deleterious effects and unintended consequences might arise? So how have we been doing this kind of thing so far? So there's this idea of microtasking, which I'm sure most of you are familiar with. And that's where you just have a kind of a delegating computer-based system that takes many tasks that are very similar and delegates them to individual humans who then provide an output, and then those are all assimilated by the system. That's exactly what we've done with our Stalkcatcher Citizen Science project. So we have just mounds of data where we're trying to look at capillaries in a mouse brain to help advance Alzheimer's research that is about blood flow in the brain. And some of these capillaries are flowing and some are stalled. It's very hard for a machine to do this very well. So we use the machine to help us isolate capillaries, farm those out to human volunteers, and then humans will then look at videos of these capillaries and make a determination of whether they're flowing or stalled. So this is an example of microtasking. And this has been very successful. The project's been around maybe 7 years now, and we have over 70,000 public volunteers. On any given day, we have 50 to 150 different volunteers engaging, and we're accomplishing the research about 5 times faster than Cornell University was able to do in the lab. It was basically an analytic bottleneck that was slowing their progress. And so previously, it would take 6 months to a year to answer research questions in the lab, and now it's only every 1 or 2 months. So it's actually enabled them to ask new research questions they otherwise wouldn't have had the capacity to ask, and resulted in several top-tier publications just based on the volunteer-provided analysis. And you can see we actually acknowledge Stalkcatcher's contributors when the journals will let us do that. It's linked to a whole list of everyone who contributed to the analysis. We're curious about whether or not, after collecting about 12 million annotations from humans, if we could try to train a machine learner and if it would do better than the first time they tried that. And they did. So the first time they tried it, the machines would get it about 85% right in determining whether capillaries were flowing or stalled. And then after we trained these machines on all the human data, then the machines were performing at about 92% sensitivity and specificity. Still not good enough for the machines to work on their own, but much better than previously. So we had this weird idea. What if we took these improved machine learning models enabled by the human data, and then we built a hybrid crowd? So we actually let these machines have agency and play Stalkcatchers alongside humans. And it turns out that the bots on their own didn't do quite as well as humans. But when we had crowds where we had a group of bots and humans all answering about the same capillary, and we combined their answers together, we actually achieved a better result than when it was just the humans or just the bots. And happy to talk later about why we think that happened and some of the details around that. It's a fun problem, but it was just an exciting result. So then another modality is these mediated workflows where we just say, hey, we can build expert-like domain knowledge into a process. For example, ethical analysis. Ethicists or people who are on IRB boards get trained to perform an ethical analysis, but a lot of that domain knowledge is procedural. So we can put that into a workflow, and then we can engage different people in that workflow in order to produce an output that's very much like what an expert IRB board member would provide. Another example of a mediated workflow, this is by a former colleague of mine, Shanti Green, who was interested in testing out some ideas about collective journalism. So the idea here was basically to say, here are a bunch of photographs from an event, something that just happened recently, and then asking people to apply their contextual real-world knowledge to evaluating those photos. And then people would contribute different interpretations of what was actually showing up there. Some people might see clues about, hey, this is happening in this state or in this city based on their own personal experience. So in the end, it was this kind of process by which you started with all these interpretations, and then people voted them up and down. The more interpretations you provided, the more voting rights you had to vote the other ones up or down to incentivize participation. And then there was a process by which all the chosen interpretations were synthesized into a cohesive article. And it actually came out remarkably well. And then another project, also by Shanti Green and her colleague, involved this sort of collaborative problem-solving idea, where a solution is defined as a pathway between an initial state and a goal state. And the idea is you can engage large populations of people in identifying all these intermediate states, spawning new nodes, evaluating ideas that other people have contributed, and then having multiple pathways between an initial state and a goal state. One of the questions that arises now as we consider emerging capabilities is how could we employ AI, for example, to contribute to the same problem-solving network. And of course, everyone's familiar with Wikipedia, which is a great example of a mediated workflow process in order to do collective article curation for an encyclopedia. This is just one very small part of the mediated process. It's their file deletion process. And of course, this has been carefully refined over years and seems to work quite well, although people who have ever tried writing Wikipedia articles might have moments of frustration. But I think the process isn't really designed to prevent frustration. It's designed to produce good articles. And so, again, the question arises, are there ways that we could insert machines into parts of this process to speed it up, to make it more fluid, or to even improve the quality of the articles that are generated, while still keeping humans in the parts of this process that are really important to ensure meaningful aspects of the content that's produced? A third kind of engagement modality is this idea of a problem-solving ecosystem. So in this case, we could imagine that there are lots of feedback loops, that we have multiple contributors, human-based and machine-based contributors, and people are contributing ideas, they're providing feedback. It sounds very much like the problem-solving system that I showed you a moment ago, and it just goes to show you that the lines here can be kind of blurred among these different approaches. But I think a key aspect to this idea is that it enables a kind of real-time collaborative modeling, and you could have real-time inputs from humans and machines in the world that are concomitant with the evolution of the model. So one idea we have for this, we call it the Open Body Initiative, that we're putting together a team and we're trying to get support for this idea right now. But the idea is that it's about collaboratively modeling virtual human. And so at all levels of the system, so biological system level, like skeletal, neurological, vascular, and so on, at the organ level, the heart, the kidneys, and at the cellular level, at the molecular level. Models like these exist in the world today, but they exist in a vacuum. And so in order to model, for example, a kidney in a vacuum, you have to make lots of assumptions about the context and build that into the model, except that kidneys don't exist in a static context. They exist in a larger organism. And it could be a diseased organism. It could be someone with hepatitis. It could, who knows? So our idea is not to actually develop all these models, but to create a collaborative infrastructure, kind of like based on this idea, where people can come together like they do in Wikipedia, but instead of curating articles together, they're actually taking their own models of physiological systems and connecting them to other models, so that then we can run simulations on those, and we can do in silico testing, for example, of new prospective treatments. And it could also, of course, be an educational tool. And so, you can, again, the question arises, how do we use AI to enhance this? How does augmented reality give us opportunities to take a ride inside a human body that's active and living and responding to different conditions, and maybe enable insights in the human being who's the traveler, to be able to actually see a cellular or molecular process unfolding, to see a protein doing something like a little nanobot, and then to have a moment that wouldn't have occurred if you couldn't actually be sort of immersed in that environment. So we've been talking about reasoning and how we can sort of think together and make predictions together and do modeling together. But all of these sorts of problem-solving activities require having some, not only textbook knowledge of the world, but real-time knowledge of the world. If we have an idea, if the world itself is a moving target. So if we have an idea, what is the state of the world? And if we do perturbations in the world, or if we're observing perturbations in the world like climate change, how do we characterize those? So just to look at some different ways that we've engaged in distributed sensing, just to kind of inspire us. Maybe some of you have heard of this, the Google flu predictions. So Google, this is kind of a famous case where they use some kind of Google Analytics to look at how people were querying Google around flu season, typing in symptoms, runny nose, fever, things like that. So based on some kind of natural language processing analysis and aggregation of these queries, they were actually able to anticipate the predictions made by the Center for Disease Control in the US by, I think, a month or so, just based on this collective human querying input. Another way we do distributed sensing is because we are sensors. We have 5 senses, some would argue more. And we go out in the world and we observe things, and then we interpret those observations and we can share those. And so, there's a project called eBird, if any of you are into birding, which is one of the most famous citizen science projects and one of the oldest ones, where people sort of collectively go out and monitor bird diversity and report their findings. And this has enabled studying migratory patterns of different birds and even, I think, identifying new species or variations that were unknown previously. Imagine that instead of binoculars, these people have augmented reality goggles on. And so now not only is what they're looking at enhanced in some way, colors could be intensified, temperatures could be visualized. Also, they could be directed by augmented reality to look more in certain places than other places if we're more interested in actually getting greater detailed data in a particular place. And on top of that, the AR is itself a sensor, and it's recording information. And it may observe things on its own that the humans haven't observed. And that kind of leads me to participatory sensing. So this is the idea that the human is the vehicle. We're not doing the sensing, but we're constantly carrying sensors around, our phones and so on. So there's this project, I think it was called, I don't know what it was called. It was about identifying potholes. So you had your phone with you, which has an accelerometer, and you're driving around, and as long as you load this app and you turn it on in your phone, then every time you go over a bump in the road, it records a pothole. And so collectively, they were able to map out potholes in a town and then figure out, where the crews needed to go and do the most repairs. And I guess this is what I already said about birding, is that with AR now and Apple Vision Pro, we're starting to, this is a really tough problem in computer vision, which is scene understanding, because it's not just about, analyzing pixels, but about putting an interpretation on top of those pixels to understand what you're looking at. One of the hardest things in computer vision to recognize is a chair, because a chair, as defined by humans, is based on affordances. It's not how it's shaped or what it looks like, it's about what it can do. So anything that can hold a person is a chair, and that's a tricky thing to explain to a computer vision system. But now with AI and the large language models, maybe that's easier to do. So then the final component here to our prediction and modeling of the world and our ability to anticipate the impacts of our solutions is about coordinated action. So does anyone know how or why geese fly in the V formation? This is kind of a curious thing. So each goose is not, it's not like they have a meeting and they say, okay guys, today we're gonna fly in a V formation. So you remember what to do. You're in that position, you're in that position. Did you have a?
I think it's a physics problem.
Yeah.
It's something about the airstream that makes it easier for the other crews to fly.
That's exactly right. Yeah. Yeah, I'm impressed you knew that. So I knew it was based on local rules, but when I was putting the slide together, I discovered exactly what you said, which is that there's this vortex. So airplanes also do the same thing, this vortex that comes off the wings. So if you fly actually directly behind a goose, and presumably you're also a goose, then there's actually a reduction in your lift. But if you fly into one of these vortices, then you get this kind of free lift from doing that. It's, like the cyclists in the Tour de France, I guess. They're sort of drafting, but it's more like to help keep them afloat. And then they take turns, too. It's not really fair if you're the front goose for the whole trip. That's the Lance Armstrong of geese up there. So they're incentivized selfishly to fly in this formation. And then there's this emergent kind of consequence, which is this V-shaped pattern. And I don't know if there are affordances to flying in a V-shaped pattern, but one can sort of think about how do we utilize local behavior to create kind of emergent impacts that are broadly beneficial. So we had this idea when the pandemic started. We realized that it's just simple napkin math. If you get a bunch of people in a room and you look at how many pairwise relationships there are among the people, those are the potential transmission opportunities for the virus. If you take those same number of people, so if you have 9 people all in the same room, there are 72 transmission opportunities. But if you take those same 9 people and you split them up into smaller groups of 3, then you only have, that's funny, I only count 9 up there, but I wrote 18. Anyway, you have many fewer opportunities for infection to spread if you spread them out. So, people needed to go to stores and get groceries and so on. So we thought, what if we could somehow, if instead of everybody going to the same grocery store at the same time, if we could distribute people more evenly across the grocery stores when they're shopping, if we could reduce infection opportunities and pandemic impacts. So we ran some simulations, and it turned out that there was sort of a sweet spot. So there were some cases where this could actually have a counterintuitive effect, but most of the time it would be beneficial. So we built an app called CrowdMeter, which is, you can see it on the left, it's an iPhone app. We're still piloting it in Ithaca, the town where we're from. But then this raises the same question of, what if you take the data that's in the app, where we tell you how crowded each store is, and then we make that part of your immersive experience? Are you going to be more inclined to actually act on that information in that situation? And if we give you a way to interact with the data and say, hey, you told me this store was empty, but it actually looks full, and I have a way to actually provide that feedback in a very immersed kind of environment. So if you take the collection of these things, if you take the kind of collective reasoning we've been talking about, and then the different modalities of distributed sensing and these ideas of coordinated action, then you can sort of start to imagine how we have the building blocks here to build a collective organism, one that can think, one that can sense, and one that can act. And if we can do that in the right way and we can do it effectively, then potentially we have an opportunity to behave more effectively, to behave more systemically, and to actually transform the world, to co-evolve with the world and to influence the evolution of the world around us. So we actually kind of tested this idea of organismic computing. This was about 10 years ago. There was no augmented reality, so we simulated it in a first-person shooter kind of gaming environment. We created a game, but there was no shooting involved. It was a hide-and-seek game. So the hiders were NPCs, non-player characters controlled by the computer. But then we had real people who were trying to find them. And so we had 3 groups. We had a control group, which we called the radio group. And so basically, they would look around, and then they just had the headset. They could talk to each other. So each person was on a terminal at home somewhere, and they would talk to each other, and they would try to coordinate their behaviors. They would say, yeah, I saw someone, they were acting kind of suspiciously, so we had to engineer suspicious behavior in the NPCs. I saw someone acting suspiciously, and I saw them around here. And so that was kind of like, this is how we do things today. So then we had a social group. So with augmented reality, we have this opportunity to surface information into the visual. In this case, they could actually text with each other, which provided sort of a record of things. People could refer back to it. And then they could actually start to map out where suspected individuals were based on their last known location. It wasn't really real time, but it was better than the radio group in that sense. And then finally, we had the organismic group, where it was more immersive, where the augmented reality was actually based on the system tracking these different individuals. So if you saw someone who looked suspicious, you could just sort of like tap on that person and say, I rate them as suspicious or not suspicious, and then everyone else on your team would instantly have that information. And when they saw that person walk by, they would see all the sort of aggregate ratings. In the end, just sort of cut to the chase, what we found is that with the smallest groups of people, the radio actually worked fine. It was the best interface. With medium-sized groups, the social interface worked best. But with the largest groups, you had the greatest benefits from the synergy that resulted from having so many eyes and sharing that information broadly. So it's a pilot study, it's a tantalizing result, but it might kind of give you some ideas about what could be possible. So these examples of hybrid intelligence building blocks and AI and augmented reality augmentations kind of just scratch the surface, I think, of what's possible and how transformative it can be. I'm hoping it will just inspire our thinking and ideation together. And I guess as we consider how to combine natural and synthetic information processing, distributed sensing, collective action, or coordinated action, does this begin to crystallize a vision of a planetary supercomputer, or maybe a superorganism that can bootstrap its own evolution? So I invite you to consider these prompts, and I'd love to learn what your own neurons collectively produce as a consequent output. Thank you.